had to reshape our program a bit since the illness of our former speaker, Agustin Moreno. But good news is we have Roman Golovko here. It's nice. And he was willing to save this episode by proposing us his talk about Lagrangian concordances are not a partial order. So I guess will be discussed on this topic. So thanks, Roman. All of you might probably know Roman is a local researcher here. So I think that's all. And thank you again for saving us from this from this seminar singularity, because it will be worse scenario otherwise.
So thanks a lot for this opportunity, and Mr. Speaker, I felt obliged to give this talk because Agustin was supposed to be my visitor. So today I'm going to talk about work which is a partial adjoint work with intercontinental result. And as Hiji mentioned, it's going to be about Lagrangian concordance. So let me start with a short motivation. So motivation. So Lagrangian cobordisms naturally appears in symplectic geometry, in particular because of the so-called symplectic field theory. Due to even time Popper. And so where one considers certain symplectic cobordisms, and in this theory there is also a relative version. So I should relative here. So we have equations manifold W with two contact ends. I don't want here 0 x lambda 1. Yes. X lambda plus, x plus, x minus lambda minus. So two contact ends. There is a symplectic cobordism between them. Let's say this cobordism is exact. So we know that omega is equal to d theta, where theta near the ends look like lambda plus and lambda minus. And for relative, we consider basically Lagrangian cobordisms inside the symplectic cobordism. And these Lagrangian cobordisms are supposed to be between the Lagrangian symmetries. There we have lambda plus and lambda minus. And one can define different types of invariants for, let's say, Lagrangian submanifolds that involve Lagrangian cobordisms of symplectic manifolds involving both like contact ends and Lagrangian ends. So from this perspective, these objects are completely natural and they naturally fit into this framework. As I'll explain later, they also provide a factorial property for certain invariants, like Lagrangian cohomology invariants that you can define for the ends of this cobordisms. So let's get to the particular questions that we would like to study. So we'll consider not all Lagrangian cobordisms, but the simplest ones, so-called Lagrangian concordances. And now let me get to the next session, which is maybe like a background. Let me say a few words about the setup. So even though the setup can be quite general, here we will consider the most basic situation, since if you can get something interesting basic situation, we can get it in more general settings as well. So we will take just, I don't know, let's say we'll consider two situations. Either we take the contact manifold of the form R3, or we have contact manifold of the form r to the 2n plus 1. So here we have coordinates x, y, and z. Here we have coordinates x1, y1, blah, 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 x7, yn, and z. And the contact forms are dz minus dx, dz minus y minus. Okay, so for those of you who don't remember or who don't know what contact manifold is just a four-dimensional manifold which is equipped with a maximally non-integrable hyperplane field. So in dimension 3, it's just a plane field. For dimension 1, and this non-integrable, maximally non-integrable hyperplane field can be written locally as a kernel of a one point. So here the one form is basically dz minus y dx, and here the form is dz minus sum of y dx. Our contact structure is given the kernel already alpha standard alpha. The kernel of alpha standard. Great. So also I should say that in general contact geometry, this type of models are canonical in the sense that there is a Darboux theorem that tells us local contact manifold always looks like that. So now in this sequence, we have this special vector field, which is called the Lie vector field, which is really simple. So Lie vector field. Typically, the vector field is given by two conditions. Whenever we have a form, in this case alpha standard, then it satisfies the properties of alpha standard on this Lie vector field R, let's say, is equal to 1, and the product of this R and our G alpha standard is equal to 2. The first condition means that it's everywhere transverse to the contact structure, right? Because for contact structure we have vanishing of contact forms, so it's non-trivial guy, right? So here we get 1, and it's also can be seen as a normalization condition. The second condition just means that the flow of the vector field preserves contact structure, and in this particular case, it's also a contact form as well. Okay, so we have Lie vector field, and here, like for this basic contact manifolds, our Lie vector field which has dc. And we'll consider Legendrians of manifolds there, so Legendrians of manifolds. So if we have a dimension 3, so in the case of R3, they will be just no-string bits. In R3 such that let me write lambda denoting this Legendrian size that Tx lambda isn't okay. So in other words, the tangent space isn't the contact structure. Okay. And in the case of R to the n plus 1, then you basically take n dimensional. The property is the same. So the Tx lambda is okay, so that's the notion of a Legendrian. For us, all Legendrians will be closed. So from now on, whatever we consider, so from now on, all Legendrians are closed. Also, I think I would like to discuss this Lagrangian concordance. Let me define the notion of this Lagrangian concordance. So let me start with R to the 2n plus 1, since it's a modular of situations in R3, just the case when n is arbitrary. So consider R to the 2n plus 1 minus y dx, basically, right? So dx sign. And from this, we form so-called symplectization of it, namely we take an extra product with R. We form d to the t dc minus sometimes I'll just not write the sum. I mean, we remember that there are these y coordinates and x coordinates, so I'll just try to use something like Einstein notation. So just avoid the sign. So just write dz minus dx. So let's reduce the amount of chalk used in this country. So let's stop writing steps. So so we have like r times r to the 2 plus 1, where we have a symplectic form. That is e to the t dz minus y dx, where t the coordinate of. And then we say that. So we say that let's say a smooth concordance. I should write it as a L e plus L minus L inside, so embedded into R plus 1. This is omega standard, standard symplectic form of the simplification. So this is a smooth cobordism, is an exact Lagrangian cobordism. So exact Lagrangian cobordism. We have the following conditions. So L is slightly sloppy, so I will write L both domain and target, right? What appears in the domain and what appears in the target, and already pick our invariant. So let me just write that L is Lagrangian, so it must be Lagrangian in this representation of the standard. What it means is that so this guy is of dimension 2n plus 2, so this L is supposed to be n plus 1 dimensional. And so Lagrangian here means that it is n plus 1 dimensional. And our form of this guy is opposite. Also, so since we have this ends, we need to deal with them. So L restricted to, I don't know, some t infinity is infinity times lambda plus, where lambda plus is Lagrangian.
So the cobordism has to preserve the orientation, or the orientation is not fixed.
Okay, so you're asking like about the notation, right? So should I go from d minus to d plus, or from d plus to d minus? I think here there is actually a logic why I write from d plus to d minus, because somehow you will have a functorial method correspond to the cobordism. But if you prefer, I can write it like that. It doesn't really matter now. Like for now, it's fine.
And the orientation are induced from L. Yeah, so
The orientation is induced.
otherwise,
Yes, yeah, exactly. But I mean, the actual question is like, how do you write the square? And this is always a matter of convention. So L and here I need to write the change plus 1, yeah. And here L restricted to minus infinity minus 3. I don't know that change plus 1 is once again minus infinity minus 3. That's lambda minus. Here's lambda minus it's Lagrangian. Is sorry, it's Lagrangian. And also, so basically we see that our L is supposed to be cylinder over Lagrangians close to positive infinity or negative infinity. And besides that, we have this exactness condition. What does it mean? So exactness just means that the function on L1, besides that, g of this function is equal to the primitive of our symplectic form. So that's exactness. Now, there is also a strange condition. Sometimes it's used, sometimes not. it's typically used if you don't make any assumptions on the ends. So in other words, on this lambda pluses and lambda minuses times some interval. So if you assume that they are always connected, and if you consider only this type of cobordism, then the next condition that I write will be not really necessary. But if you don't make this assumption, then we need to assume that our F is in fact constant on ends, on positive ends, positive ends, and on negative ends. So by ends, we actually mean this products of intervals. A priori is just locally constant, but if you want to concatenate cobordisms, if you really would like to get some sort of like a TQFT story, topological quantum field theory story, then it makes sense to make this assumption. So whenever we move the cobordism, they should have the same potentials. Basically, it's like a potential function. So great. Now, what is a concordance? So concordance is the simplest possible cobordism. So concordance is just a cobordism which is diffeomorphic to a cylinder. Okay, so concordance is a cobordism that is diffeomorphic to cylinder. Okay, so now we have this general notion of cobordism, we have this notion of concordance. Let me maybe try to explain what we would like to prove. So the theorem for us today is the following. So maybe before I write here, let me also say the following. So given a concordance, let's say from lambda minus to lambda plus, what it means is basically we have this cylinder, right? So it's supposed to be a cylinder. We have this cylinder satisfying all these properties. So in other words, we have this like honest cylindrical ends over lambda plus and lambda minus. That's when we say that there is a concordance to lambda minus, right? So whenever we have this type of concordance, we can actually define the relation. We can say that lambda minus is I don't know, concordant to lambda plus. Okay, just like in a circular relation. Okay. Now, one can easily show that this type of relation is reflexive. So this relation is reflexive. And that's really simple. And this is like the first example of a Lagrangian concordance, how one can get something like that. So there is a general principle, a general fact saying that if there is a Legendrian isotopy, in other words, one parametric deformation of a Legendrian submanifolds, then this Legendrian isotopy leads to the Lagrangian concordance. Okay, so given a one parametric family of Legendrians, family of Legendrians, let's say lambda t, we say that there is the isotopy, Legendrian isotopy, and whenever there is a Legendrian isotopy, there is a result. I think there are many people whom I should write. I mean, it appeared like in many places. So in particular, I can write, let's say, Shangham, Elefort Gromov, Echo. So basically, there is a result saying that existence of Legendrian isotopy implies the existence of Lagrangian concordance. So Legendrian isotopy implies Lagrangian concordance. Lagrangian concordance.
The family is supposed to be local.
What do you mean by local?
It cannot be circle. T cannot be from circle.
T from 0, 1.
0, 1.
Yeah, I mean, yeah, that's of course what I mean. Yeah. So T is from 0. As usual, when we define homotopy, isotopy, blah blah blah. So this is just stuff. So one parametric family from 0, 1. So there is a standard result saying that if you have a Lagrangian isotopy, then there is a Lagrangian concordance. There are several constructions. They're almost, I mean, okay, they're similar to each other, let's say. And from this perspective, we see this reflexivity, right? So whenever we have Lagrangian isotopy, we always have a concordance, right? So in other words, you can say that lambda is concordant to lambda. Yeah. So
implication or equivalence? Is it implication or equivalence? Once you have concordance, then you can find isotopy.
no, there are concordances that are not coming in isotopes. So
If you do the local compactification, the reverting the dimensions, then if you go from symplectic by compactification 1 dimension less, but it's totally local. So
compactification means that you go up, not down.
yeah, but locally,
Maybe I don't understand this question also. Yeah.
it's not correct.
Okay, so everything is connected. Connected, as I say, and closed. So please ask connected questions. I'm just kidding. So
Well, I guess you can also do this business when your target space is not standard symplectic structure on R to the power. It could be some symplectic manifold.
one can consider general symplectic cobordism, as I say, so somehow, so far I'm just describing the most simple situation. Doesn't mean that it will not work for like more general setup, but I'm just trying to formulate at least what I want to do. So from this perspective, it makes sense to consider the simple situation. One can definitely generalize.
But this relation, will it grow or will you find
Which one?
just you did? Yeah.
For reflexivity, you'll always have it. For reflexivity, you will always have it in particular because like there is always a Darboux ball. As far as your Lagrangian isotopy doesn't escape the Darboux ball, the same type of principle will work. Because somehow, basically, I mean, okay, thinking about this R to the 2n plus 1 and symplectization over it just means that we are working in some like a local story in some Darboux ball, right? So every contact manifold looks like a whatever. There is this like a Darboux ball representation also for symplectic manifolds. There is also like a local principles that allow you to see it as a part of the Euclidean space. So now, so we have this reflectivity. One can also easily see. So there is also transitivity. Transitivity, and this is obtained by just stacking concordance. Okay, so broadly speaking, you can do the stacking. Oh, I don't know. You have one concordance from lambda, let's say 1 to lambda 2, and you have another one from lambda 2 to lambda 3. Then somehow you can identify them. So you have a concordance from lambda 1 to lambda 3. Smoothly, it's okay. What comes to the Lagrangian story, you need to play a bit with the coordinates here because here you have basically like a positive infinity, there you have negative infinity, but we still have this vector field given by the symplectization direction. So somehow it's just a matter of like smoothing it up so that you get the right coordinates and everything works. So great. So we have transitivity. Now somehow what we want to show, so the theorem that I would like to present is that Lagrangian concordance does not, or maybe Lagrangian concordances do not define an antisymmetric relation, and hence and hence Lagrangian concordance. Lagrangian concordance. Concordance is not a partial. It's not a partial. Okay. So just to recall what it means to have partial order. Partial order, we need basically this reflexivity, we need this transitivity, and we also need to have this antisymmetry. So antisymmetry just means, or whatever is said here, just means that it's possible to have a situation of lambda minus is in relation with lambda plus, with concordation. Lambda plus is in this relation, concordation with lambda minus, but lambda minus is not exactly an isotopic. Isotopic to lambda plus. And the question about this antisymmetry was in the air for quite a while, since the times when the Lagrangian concordisms and concordances came to play, maybe already for 20 years, so this was like a reasonably old question. Now we solve this theorem, so I need to say where we solve it. So first of all, we solve it in dimension 3, and as the result is Jurgis. So if dimension of so if n basically is equal to 1, then it's joint with Jurgis. With the interval is also then 7. Since Jurgis is not here, I'm allowed to shorten his name. Maybe he will watch video recording, but probably not. Anyway, if he does, sorry, Jurgis. So once again, I'm trying to reduce the amount of chalk, the consumption of chalk in this country. So right, just DR. So and now there is also a continuation of the story. Unfortunately, I don't know how at the moment how to do a general case, but I can get the same for n equals 2, where k is good. So there are basically two cases where it works. In both situations, here we speak about r to the 3, and here we have r to the basically 4k plus 1. Okay. So now let's see how to get something like that. Staging proof. H. So there are a few things that I need to explain when I go there. So first, let's consider the situation when n equals to 1. So in the case when n equals to 1, of course, we speak about this Legendrian knots and links. So let's even like consider just knots. So here we consider just Legendrian knots. So let me recall that or let me say for those who don't know, let's say if you consider Legendrian knots in R3 is X, Y, and Z coordinates, then it's natural to study them using so-called from diagrams. So we can consider so-called from diagrams. We take its projections, so we have 5 from R3 to R2, so where we just forget about Z direction. Where we just forget about Y direction, X, Y, and Z is mapped to X. So now if you take a node and if you take its projection, then of course you will get some diagram. So this Legendrian condition makes some restrictions on the diagrams that you could potentially have. So whatever we will discuss here will not be just a classical node theory, it will be a node theory with some extra information. So somehow the diagrams that are allowed will not have, so whenever we consider XZ plane, so they will not have vertical tangencies. They will have cusps as singularities. They'll have only double points. And we always have this condition that the overcrossing will have a slope which is smaller than undercross. Okay, so let's say like this. This type of crossing is fine. The only singularities are with this form. Okay, so cusps. And the only crossings that you consider are double crossings. So this is the standard, let's say, Lagrangian unknot. This is the Lagrangian unknot. There's a left cusp and right cusp. And let's say if you ask for trefoil, then I don't know, there are several ways to draw it. Here. Something like that would be a trefoil. There's another presentation that I can draw, but okay. So the pictures like that define the Lagrangian knots. Now, what comes to Lagrangian coordinates, I also need to present the pictures that correspond to the deformation of diagrams and that are known to describe sort of Lagrangian coordinates. So let me show them. You can always ask, you can also ask like, okay, so in general knot theory, let's say for standard knot theory, there are this like Reidemeister moves that describe like local moves that are allowed for standard diagrams. Is there like any analog here? Yes, it is. If you ask me to draw it, I will draw it. So basically the pictures are really, really similar. So there are like there is an analog of Reidemeister moves. The Lagrangian story as well. No. Okay, so what do you know about Lagrangian coordinates for this type of diagrams? So it is known that if you do this type of move locally, so here, so you see whenever we have this XZ diagram, right? So this is your X and this is your Z. All these vertical lines, they are read ports. So they are ports of three vector field, which is DDZ, right? Which start and end the collision. And now there will be a move which says the following. So whenever we have a read port, okay, so this type of like vertical line, you can substitute it with a local picture of this form. And this type of story corresponds to a certain surgery, and it will give us a pair of planes coordinates. Okay. So it's like a pair of planes coordinates. This guy corresponds to a pair of planes, it's a Lagrangian coordinate. Then we already know that Lagrangian isotopy. We already discussed this. So Lagrangian isotopy, i.e. from the point of view of a diagram, so all analogs of Reidemeister moves.
What is the surgery called?
What's that?
How is the surgery called?
It's called the Lagrangian surgery or ambient Lagrangian surgery, right? So in dimension 3, it's a typical name is like a Lagrangian surgery. Here it's like I think Lagrangian surgery. It's a dimension is higher than 3. So Lagrangian isotopy, i.e. all analogs of Reidemeister moves for Lagrangians are realizable. Right. So you know that for Legendary isotopy, as you mentioned, you can write Lagrangian concordance, so how everything is realizable for Rademeister move, since every Rademeister move, every isotopy can be decomposed into Rademeister move, as is the standard knot theory. Right? So this is like a type 1, let's say, this is type 2, and also there is type 3, which is really basic. So you have unknot. So this is so-called TB minus 1. I'll explain in a moment what it means. TB minus 1 unknot. And we can take its cut. So it's like a Lagrangian disk. Lagrangian disk filling of. So basically, at the level of diagram, it means that you have something like that, and then it disappears. So you simply, I don't know, maybe I'll write some sort of set. Right? So you don't have anything at the level of this. Now, all the moves, so here, this type of move, even though I write it from left to right, since I'm European, I can write it from up down, right? So if I would be Japanese, right? So honestly speaking, this type of picture corresponds to, so this direction, this is the syncretization direction, right? So this syncretization direction. Right, so this guy is a syncretization. Now I like it, so probably I should consider myself Arabic. It's not going from right to left, but okay. Yes, I should like. Great. So that's it. Good. So we know all these local pictures. They correspond to coordinates. Now, in order to proceed, I also need to say. I need to say a few things about invariance. So basically, with this type of story in mind, we can define like basic invariance. We can define so-called TB and R. So TB is typically called the Thorstone-Benneken number. And R is a rotation number. In high dimensions, it becomes class, but okay, rotation number. And at the level of these diagrams, these simple diagrams, it can be defined in the following way. So Thorstone-Benneken is just a Winding number, or in other words, number of positive crossings minus number of negative crossings, and then minus 1/2 number of cusps. And what comes to rotation number, you can also write it down. Locally. So yeah. So it will be 1/2 number of so-called downward crossings minus number of upward crossings. So what does it mean? So let's consider this basic example. So this unknot. Okay, so for TB, we don't have any crossings, so neither positive nor negative. So typically, let's say, in order to speak about positive, negative, and in order to speak about TB and R, in fact, I need to add some orientation to the diagram, right? And positive crossing just means that whenever I have overstrand, I try to get to understrand, I can just move with a 90 degrees move, right? So I'm taking the positive move, which is 90 degrees, and then the step crossing is called positive. And then if I have something like that, let's say, i.e. the shortest move is in fact in the opposite direction, or you need to or we need to make this like a big angle move, then it's a negative, right? So that's for crossing. But here we don't have any crossing, so somehow this number is 0, and then the number of cusps is 2 here, right? So somehow TB is equal to -1. That's the reason why I wrote -1 here. Now what comes to R, once again, so here we have some direction, and now we are speaking about downward cusps and upward cusps. So downward means you go down, upward means you go up, right? So here you see that R is equal to 0. TB -1, R is equal to 0. You can compute them for arbitrary time. Now, what is known is, let's say, for Lagrangian concordance is that, and in general for cobordism, that TB of lambda plus minus TB of lambda minus is equal to basically minus. In higher dimensions, it will be also a certain sign, not just minus, but -1 to a certain power. But here we have just the Euler characteristic of our Lagrangian. Yeah. So in the case of concordance, this number is equal to 0. Hence, for concordances, so TB of lambda plus is equal to TB of lambda minus. So for concordances, TB of lambda plus, TB of lambda minus. And we also know that R, we always know that R of lambda plus is equal to R of lambda minus. So from this perspective, this concordance is a kind of difficult to deal with because like Legendrian invariants for the ends are the same. In particular, it's a difficult question to study. And also we will need this number slightly later on the construction. Now, also with this type of features for the for these cobordisms, I should say the following: that if you can get a cobordism coming from these three pictures, right, coming from their combination, then you say that this cobordism is decomposable. In other words, we can decompose it into simple pieces. The decomposable cobordisms are those that are given by combination of one twins. Okay, and now we are ready to go. So let me provide examples that contradict antisymmetry in dimension 3. Then we will discuss how to show that they actually do. How much time I have?
About 50 minutes, I guess.
Started.
Yeah.
Exactly. Yes. Okay.
Not exactly.
So we are ready to provide the arguments. Now I hope we'll be ready, able to draw picture really quickly. For the picture, if I would like to draw, it's like okay, so I'll stop forgetting about like upper, like overstand and understand because I know that the picture is always like that. So I will stop caring. We know that all the crossings are like that. So this. Something like this. So it's supposed to be a mirror of 9 to the 6. Now, the point is that if you perform, well, here you have this form, okay, that we described there, yeah, that we described like using the person. Then whenever you do something like that, right, so whenever you use this cobordism move, by following this diagram, you can actually get to the situation, and here you will have to unlink unknowns. And then, whenever we tap up one of the guys, we will have a concordance from unknown to mirror of 926. Okay. So we know, so it's clear, it's simple to construct. So there is a concordance between unknown. So I'll write it as U. So this is a standard Lagrangian unknown. And I'll write lambda M926 for the Lagrangian representative of this mirror of 926 function. So there is this guy. Now, Baptiste Champagne, using so-called bilinearized Lagrangian contact homology, proves that there is no concordance. There is no concordance the other way around.
Lagrangian concordance.
Lagrangian concordance, yes. So there is no Lagrangian. I mean, smooth concordance is of course there. So you see the point is that, so what is interesting about Lagrangian concordances or Lagrangian coordinates, there is a symplectization direction. And we have a symplectic form which has e to the t there. So it's really important what is the direction of this t, right? So whenever t goes up, whenever t increases, the volume or the area increases. Whenever t goes smaller, the area is smaller. So you cannot revert. Somehow there is no way to revert this guy. So in particular, this is one of the examples when we see non-symmetry of Lagrangian concordances, right? So this way you can see that there is no symmetry. This example of Baptiste explains that there is no symmetry. I will not say how it's proven, but here you actually need to play a bit with holomorphic curves and sophisticated variant. But anyways, that's what Baptiste proved. And now the point is the following. So with Yorgos, we basically proved the following theorem that led to the result that we want. Theorem that says that whenever we have a decomposable, so given a decomposable concordance, Lagrangian concordance, and its formal reverse. So in other words, so let's say if you have a concordance of the form T, X, Y, Z inside, I don't know, R to the 4, right? Where the first T is our symplectization direction, then what we can do, we can just reverse it by doing this. It will not be a Lagrangian concordance. It will be just a smooth concordance, but it will not be Lagrangian. It will be like that. What we mean by like a formal reverse. So whenever we formally reverse it, then this formal reverse admits a smooth isotopy. And its formal, okay, so given a decomposable Lagrangian concordance and this formal reverse, let's say this formal reverse is, I don't know, C minus 1, then C minus 1 admits maybe is compactly isotopic. Isotopic is a totally real concordance for an arbitrary almost complex structure that we can define as this symplectization. For arbitrary almost complex structure. So for those who don't know, almost complex structure is just endomorphism of tangent bundle with the property that its square is equal to -1. Totally real means that whenever we consider tangent space, then if you have almost complex structure and act on this tangent space and we intersect with the original tangent space, then we get 0. So that's totally real story. Now, this way we can get to totally real in the same smooth isotopy class. And now the point is that totally real concordances, as it turns out, as we studied, so they satisfy H principle. So in other words, whatever you can do, so basically whatever you do smoothly with them, you can do in a totally real way. Okay, so somehow smooth isotopies, smooth formal isotopies lead to the totally real isotopies. And after that, we actually proved that totally real isotopies will approximate Lagrangian, or totally real concordances will approximate this Lagrangian concordances if you so-called stabilize ends. So for that part, in fact, we need certain like hard techniques.
I'm sorry, I'm not missing the word real in the
Then C minus 1 is compactly isotopic to the totally real concordance for arbitrary almost complex structure.
Oh, so totally.
Totally real, as I said, so totally real just means that you have almost complex structure, okay, on this, I don't know, on the syncretization, okay, and almost complex structure means that G is a endomorphism of tangent bundle, okay, such that J square is equal to minus identity, yeah, and then we have J of TL intersection with the L is equal to 0. So this is the totally real condition.
Okay, fair play.
So now there is a way, as I said, to go from totally real to Lagrangian. And that's basically the approximation that Jorges did himself. So basically the statement is given a totally real concordance, so if C is totally real, then so informal result of Jorges is that whenever we have totally real concordance, then we can deform it to a Lagrangian concordance. That's it. Here we have totally real concordance from lambda minus to lambda plus. Here we have Lagrangian concordance from so-called stabilization of lambda minus to stabilization of lambda plus. Well, stabilization is a Coulomb operation. So let's say here we have the standard from diagram, something like that, and then you can perform either this type of move, or you can perform this type of move. So there are two ways to stabilize. But locally, you add a zigzag of this type. So this type of zigzag will change the invariance RNTB that we described in particular. So we add some number of cusps. Okay, so somehow it changes the Legendrian isotopy type, and different zigzags have different behavior. Let's say, so R for one of them increases by 1, and for another one decreases by 1, and TB always decreases by 1, because like by the definition of TB, we have -1 minus the total number of paths, so somehow we always decrease. So you can say in particular that Legendrian doesn't have any it's not stabilized, so there is no there's nothing like that inside if TB is maximizing. Okay, so if you have like a maximal invariant. Anyway, so this is the stabilization, and that's what we do here, right? So whenever we do the stabilization, so whenever we have totally real concordance, we can get to the Lagrangian concordance with the defect that in fact we do stabilizations with that. Okay, now for something like that, so if you apply it to the examples that to the Baptiste example, basically, right? So we can say that there is U, there is this lambda mirror of 926. So we know that we have a concordance here and here. So since we in fact know that this type of concordance was decomposable, yeah, so we can take its formal inverse and we can use this approximation, right? So first from smooth, from whatever formal reverse to the totally real, and then from totally real to Lagrangian. So here we have some stabilization of this lambda mirror of 926. And here we have stabilization of U. And we know that there is concordance this way. And now there is also extra story. I think it was also shown at some point by Baptiste. So Baptiste, and actually it can be done locally, like by everyone. It's not really a big fact. So Chantrain, in particular, in one old paper showed that if lambda is concordant, we need to write here. So if lambda is concordant, if lambda minus is concordant to lambda plus, then stabilization of lambda minus is concordant to the stabilization of lambda plus. So in other words, we can transform this guy into stabilization. Here 936. And here we have a stabilization. So you have this direction, and you have that direction. So you have concordances in both directions. And these guys, they are different smooth isotopy classes, right? So hence they cannot be Lagrangian isotopic. Hence we get a contradiction to anti-symmetry. Does it make sense? Sometimes. So that's a way we get a counterexample in dimension 3. Once again, we started maybe like 5 minutes later.
Yeah, but we don't have to stick to exact times. If you have said anything,
if there are any questions, I can describe what happens in high dimensions. So it's
thank you very much. Let me open the discussion panel if you have any questions.
Yeah, what's happening?
Yeah.
Expected one.
That's unexpected question, so thanks a lot. So it turns out, so first of all, why we don't consider all dimensions, right? Why only even guys? It turns out that, so in high dimensions, there are special submanifolds that are so-called loops. So loose submanifolds, they satisfy H principle. So in other words, for a set of invariants, for a given set of invariants, if you fix it, then like let's say in almost all dimensions, whenever you perform a smooth deformation, you can perform the same type of deformation in a Lagrangian. Okay, so there are so-called Lagrangians. Typically, they look like so their front projection looks like a big enough fish. It's like a fish for X, Y, Z space. And then you take a product with a cotangent bundle where there is a certain whatever inequality that describes the size of the tent where this fish lives. So it's like a space, and the Lagrangian in the space looks like this fish times 0 section of the cotangent bundle, and everything looks like this 3 space times the cotangent bundle itself. Okay, it's like a fish in a big enough tank. So think about this fish as a piranha, basically, right? So whenever it appears, it kills all contact geometries. So in other words, it will start self-reproduce. So this will guarantee its H principle, and somehow it will kill all modern invariants. So whatever you can do with, I don't know, holomorphic curves will die there. And the point is that, so these loose guys, for a given, so if our m is equal to k, then it turns out that in this dimension, our TB, our Thurston-Bannikin number, or its NL, is completely topological. In other words, TB of lambda is something like a 1/2 times sine times, once again, the earlier characteristic. So it's not interesting. TB is not interesting at all. It's just a topological thing. But the point is that whenever we fix R, there are exactly two loose Lagrangians such that and also we need to assume that for simply connected lambda. So it's simply connected lambda. So as far as we consider just simply connected Lagrangians, then somehow there are exactly 2 for 1 R. Now, whenever we fix this set R, TB, and the smooth isotopy class, there are exactly 2 Lagrangians. Now we also can do the following. So there is a result of Elliott, Burton, Murphy that allows one to have so-called so they prove that there is a H principle for Lagrangian caps. So in other words, we have cobordisms with a loose Lagrangian negative answer. So here we have like let's say here we have, let's consider spheres. So here we have S1 and S2, two spheres. And they prove that there is an H principle. Whenever we have S1 and something here, okay, let's say smooth coordinate, then you can always deform it to become exact Lagrangian if you know that S1 is a loose guy. Yeah. So it's really easy using this like H principle to get exact Lagrangian coordinates with negative lengths. And now we perform the following. So we basically take this type of story for S1, S2, and for S2, S1. Okay, and we apply this H principle because here we know that we have looseness, we apply it, in the end of the day we will get exact Lagrangian. You can say, well, I mean, how do we know that there is actually a smooth coordinate in order to apply something like that? High dimensions, there is a standard result of Hatriger, says that we have always an isotopy. From isotopy, we can get a smooth concordance. So there is always a smooth concordance. So using the first result of Hatriger, then H principle of Elliott-Berg and Murphy, H principle for caps. We can get this type of guys. And we know, as I said, by the result of Murphy that there are exactly two. So this is like exactly from Murphy. So that in this dimension we have exactly two loose guys that are not legendary and isotopic. So this way we will have two exact Lagrangian concordances from S1 to S2 and from S2 to S1. And this guy is not legendary and isotopic, hence we get the counterexample to antisymmetry. Okay.
And for N4?
For N odd, we know that there is exactly one loose guy. So then it's much more complicated. And okay, so let's say this way. For concordances, at the moment, I don't know how to play this game. But I know how to get examples if you consider not concordances, but coordinates. So at some point, there was a we first constructed this so-called non-cylindrical coordinates from the guy to itself, so-called non-cylindrical endocoordinates. And let's say in dimension 5, in contact dimension 5, maybe for legendary dimension 2, we had this type of picture. So let's say you can write a torus, legendary and torus. If you wish, it's obtained from the unknown and when you rotate it, right? So it's called span of it. And then you perform a certain surgery with respect to the disk, and you will get a torus. Okay. And then you add a handle once again, and you will get a sphere back. This guy is the same thing as the standard sphere. This guy, this guy is a torus. This guy is a torus. This guy is a sphere. This guy is a torus. So basically, I mean, this type of phenomena exists since we can perform this kind of constellation. Right? So this way you see that there are cobordisms both ways, and they are just not smoothly isotopic, hence once again. And the cobordisms here unfortunately are not concordances, so something happened there. But you see that there is no antisymmetry. Now from this example, you can do the following. So a long time ago, I proved that for Lagrangian cobordisms, you can perform this like a spinning constructor, whatever. You can spin them, you can take a product with, I don't know, with spheres, so that you lead them to high dimensions. And now taking this picture and taking the products with spheres, and spinning them, you can get to arbitrary dimensions. So, and you don't care really about the whatever, whether the dimension is even or whether n is even or not. But of course, here the problem is that you are not talking about concordances. These are cobordisms. When it comes to concordances, I don't know.
I would have a very basic question.
Yeah.
You mentioned many times H principle. Could you please recall and tell me what's H principle in a general setting? Or
okay, it's a difficult question. It's okay. So first of all, like in Cerny, there was this.
Okay.
So roughly speaking, the point is you have equation, certain equation. So in particular, you can write equations that corresponds, so where the solutions are supposed to be, I don't know, Lagrangians or Legendrians. It's always a matter of writing differential equations. And then you try to solve it. And it's really difficult to solve it, but you can solve it up to homotopy. And that's exactly H principle. So whenever you can solve it up to homotopy, you say that H principle works, okay? And then you actually need a certain condition which says that So if you can solve it up to homotopy, then basically the formal solution will be actual solution. Okay.
So in this case, how does it apply?
Here.
Yeah.
So you have a smooth concordance.
Mhm.
So I know definitely that there is a concordance, let's say, from S1 to S2, smooth one. Coming from this result that in high dimensions, if I consider guys of the same smooth isotopy class or whatever, they're given basically by the embeddings of the same manifold inside whatever R to the right power, then there is an isotopy between these guys. Yeah. So if there is an isotopy, then we have a smooth concordance.
Mhm.
So yeah, I know that there is a smooth concordance. I know how the ends look like. So the ends, they will be just cylinders over Lagrangians. They will be exact Lagrangians near the ends, right?
Mhm.
And now, once again, I know that negative end is loose. And I know that there is a H principle for these guys of Edgeberg and Murphy. Hence, I can isotope this concordance so that it becomes Lagrangian concordance, preserving the ends. I mean, the ends to be potential like Legendrian isotopic, but since we consider everything up to Legendrian isotopic, they will not change.
Yeah, because isotopy is some kind of homotopical transformation. Am I right?
Isotopy is a smooth, basically, it's like a smooth homotopy.
Okay.
Yeah.
Makes sense.
So basically, you use for this Lagrangian isotopies the principle of Lagrangian concordance. Yeah, sometimes or the principle, the results which are known for Lagrangian. You actually at the beginning, actually, you mentioned the theorem about Lagrangian isotopies and Lagrangian concordances. Which connect them, yeah. By
So Legendrian isotopy implies Lagrangian concordance.
only this way.
Yes.
Only this way.
And as I mentioned, you know, these things, yeah.
If you don't have Lagrangian, it means that you don't have this Lagrangian.
No, I mean, that's precisely the way to see, for example, isotopy. That's not, to see concordance, that's not coming from isotopy. So there is a concordance from unknown to the mirror of 946 there, and they are not even smoothly concordant. They are not even like smoothly isotopic, right? So there is a concordance from U to the mirror of 946, and there is no Lagrangian concordance.
Just, okay. I understand this.
Sorry.
Was it connected to the Lagrangian the Lagrangian concordance was for the for sure for the symplectization of the Lagrangians
Yeah.
manifolds?
Can you say it again? Sorry.
The concordance of Lagrangian manifolds was meant for those
Concordance of
Lagrangian.
Lagrangian. You mean of Legendrian? Concordance between Legendrian.
Yeah.
Lagrangian concordance. Yeah.
Lagrangian concordance was
Yes.
for such Lagrangians which are symplectizations of the standard symplectizations of the Legendrians. So I have Legendrians, I'm on some isotopic, then I do standard symplectization procedure, and I speak about Lagrangians, and about them I know something about their concordance or
Once again, the point is,
isotopy or isotopy.
I said,
And so it was only in apostrophes for this construction of symplectization going dimension back for the specific. Or how in the theorem the Lagrangians are determined by the Legendrians.
how Lagrangians are determined.
Yeah,
by
because just for
Legendrians.
example, isotopies between, let's say, two fixed Legendrians.
Yes.
And then the theorem connected it, or you connected the theorem
Yes.
to the concordance of Lagrangians.
No,
Lagrangians.
so concordance between Legendrians. So once again, you consider Legendrians in a certain context space. You consider symplectization, which means basically a symplectic, basic, like it's
Product.
trivial symplectic cobordism from your compact vector space, the compact vector space. That you have this Legendrian still there. You can consider them at positive and negative affinity, and you consider Lagrangian concordances between
the Legendrians.
Between the Legendrians. Yeah, exactly.
Yeah, so it's in this way.
Yes.
Mhm.
You have Legendrian.
Okay, so
Lagrangian.
they stay the same.
So Legendrian is it's like a
Yeah.
basically like a boundary condition for the Lagrangians inside
I thought that
simplification.
everything goes one dimension bigger. Also, the Legendarians are simplified. They are made Lagrangian submanifolds, and then you speak about Lagrangian isotopy.
Okay,
So it
so
was my mistake. I didn't,
okay, so
that is theorem.
let's say it this way.
Wow.
If we consider exact guys, right? So whatever concordances, they are automatically exact, but whatever what comes to cobordisms is not always the case. But let's say we are talking about exact Lagrangians. Okay, so if you consider contactization, you can leave exact Lagrangians to Legendrians. So if you wish to consider Legendrians, it's also fine. And if you want to consider Legendrian cobordism between Legendrians, it's also fine. And we can consider Lagrangian cobordism between Lagrangians in the sense of arguments. So there are different types of cobordisms. But
the
yeah.
homotopy was Lagrangian, if I say it this way.
Yes, but the homotopy of Legendrians gives you Lagrangian.
Yeah.
Yes, exactly. So, and only this type of cobordisms between Legendrians, so Lagrangian cobordisms between Legendrians, so it naturally fits to symplectic field theory. The other ones, like Lagrangians between Lagrangians, so in the sense of Arnold, they are not. So Legendrians between Legendrians, they are, I mean, in certain situations you can relate them, but you know, one needs some extra assumptions.
Okay, thank you. Any other question? I'm not sure if I want to ask this, but it's a very nice question. Do you think there is any chance to characterize concordances or Lagrangian concordances via algebraic invariants, like these numbers you mentioned? Or
so I mean, okay, so as I said, so a priori. So first of all, you're asking about the question of classification. Even in the simplest situation, I don't know, here of course we are speaking about like a Lagrangians that have cylindrical ends. This is like even more sophisticated story. But if you consider, let's say, closed Lagrangians and simple spaces like CP2 or whatever, still there is only a conjectural classification up to, let's say, Hamiltonian isotopy. So we know that there is an infinite family of whatever Viana tori, like a monotone Lagrangian tori, up to Hamiltonian isotopy. They're all different, but we don't even know that you know whether this type of family describes everything. So algebraically it describes everything, but geometrically we don't know. So even in the simplest examples, it's really like difficult to say what is there. So that's the point somehow. So geometric objects are really difficult to classify. And that's the reason why even in the simplest situations, there are these natural questions of like what type of like behavior or what type of properties this like a basic condition or whatever, this basic relation between Lagrangian concordant has. So like, is it symmetric? Is it anti-symmetric? Does it define a partial order and things like that? So, you know, all these questions are really basic. They're simple to formulate, but quite difficult ones.
I guess. Okay, thank you. Is any other question? No, it's the case. Let me thank you again. And Roman, you can say what will be next Thursday.
Yeah, so next Thursday there will be hopefully coming visitor. Once again, my visitor, hopefully he will come. So his name is Vincent Miliev, and he is from Sorbonne, and he will speak about, I think, something like a differential, like a DG coefficients in Morse and Floer's theorems.
Yeah, I will specify it in coming announcement via email. Thank you.